All right, everybody, we'll go ahead and get started. Just a heads up of like where we are in the content. Is it at all weird for the people here to look at me up there and see me looking at you, but you're looking at me on the, anyway. What we're gonna finish up today will be enough to finish the rest of homework 3. Homework 3 is due, I think I put it either Friday or Monday. I can't remember which one. Which one is it?
Monday.
Monday, yeah. So this will cover everything that you would need for that. We'll refine some of the ideas and practice them a little bit more on Friday, but this will introduce all of the major ideas that you need. The plan for the midterm is Monday to Monday of next, so it comes out right when homework 1 is due, and then you've got until the following Monday. And I'm not gonna double up another homework on top of that, so you'll just have that full week there to do the midterm. You'll be able to work in teams of 2. I'm also gonna put a little survey up on Canvas in case you want me to randomly assign you a teammate. I can do that as well, but you can also find your own teammate, or you can also work by yourself. Whatever you feel most comfortable doing is fine. Those concepts on the midterm, it'll kind of build on this simulation that we've got here. You'll need some of the ideas from the previous stuff as well, but I think when you see it, you'll recognize the similarity to what we've got here. Oops, I forgot to plug in my other laptop. As far as where we're going, today we will finish the basics of our ideal gas simulation, and then over the next week and a half, we'll sort of enhance it, right? We'll make it, A, a little bit more realistic, so we'll add more and more particles to it, but B, we'll see other ways to do the same kind of coding that we've already done that are a little bit faster. Not so much for the computer, well, actually, yeah, it is faster for the computer as well, but it's also a little bit cleaner for us too. There's not so many nested statements that are on here. So we'll go ahead and get started. If you're watching on Twitch, I'm over on Canvas chat too, so if you have any questions. And anyone here, if you don't feel like speaking and being recorded, you can throw your question in Canvas chat, and I will see it over there. Oh, and the lab hours tomorrow, those are both Zoom and here. So you can either physically show up during any of those 2 hours and I'll be here, but I will simultaneously be on that same Zoom room that I've been in before, so you can do either one, whichever you feel like doing. Okay, let's review that Matlab script really quick, and then we'll take some notes over in Excel to see the concepts that we need to code, and then we'll code it up. This is where we had stopped on Monday's lecture. We had divided the script into 3 big chunks. There was the initialization part, which was setting up initial positions and velocities and the vectors that we needed here in order to store everything. We had mentioned that we could have done this with matrices too, but as we'll see towards the end of today, this was the better route because the matrix would get confusing when we have more than one particle. And then we had to set the initial positions because unlike the random walk, we are now starting at somewhere other than 0, 0. So we had to set those first ones to 0, 0. Then we did the simulation, which again, for us is an iteration. We got the old values, we calculated some new values, and then we plugged those new values into that vector of all zeros that we had. And I had mentioned that it wasn't necessary to split those into separate pieces. We could have made a statement like this one where we do it all in one line. As we'll see here, when we have to make decisions based on those calculations, this is a little bit more convenient when we've got them split up like this. But this was also an option for the simulation we made last time. And then we did some plotting down here. The problem that we had experienced, which I'm just going to set these, well, let's run it just so we can see it. So this was our simulation, and we had sent it towards the end of class way off to the right, and we had noticed it ended up hitting the wall. And I'm going to mess with the numbers a little bit. What I would like is for this to be over by the right wall and kind of headed up and to the right and eventually hit the wall, just so that we can then sort of analyze that system over there. And this is another sanity check you can do when you're setting up your code, right? I can say I want it to be near the right and going up and to the right. Let's see if I can guess the values that I need for that. Let's put this one over at 8.2 for the x and maybe 2, 3 for the y. U for 0.4 is fine, and then maybe we'll go, I don't know, 0.3 for v. Pretty close, right? I wanted it over on the right and stepping off. This was one of the many problems we had found in our simulation was what happens when we're off to the right like that. The area that we're interested in, we don't really care what was happening in between these first two. Those worked well, right? They were inside of our domain, everything worked fine. What we're worried about is this point right before I stepped out of the domain, right? I need to be able to recognize those points when I step out of the domain, and those are the only ones that I have to worry about. Somehow I have to flip stuff around. So that's what we're going to do over in Excel. I'm going to show you the explicit math that we need to correct this particular problem, and then we'll code that over here in Matlab, and then I'm going to turn you loose to code the other 4, or the other 3 after that. So let's go back over to Excel. We will first take some notes. We'll just say theory. This part, again, this is, I don't usually expect you to do any particularly complicated math, or if I do, I'll do an example like this where I set the whole thing up and show you one way to do it, and then ask you to do a similar version somewhere else. So this type of derivation I wouldn't expect you to know, but when I show you something like that, I would expect you to be able to apply it with, like, instead of the right wall, can you do it with the left wall? Something like that. So let's look at focus on the right wall, and we'll say this is the wall. And that wall exists, in this case, at x is equal to 1. That was our right-hand side of the wall. Our particle, let's say we started out over here. So we'll call this x old. And I'm only interested in the x right now. You'll, I think, see how the y changes here in a moment, and we'll show you that. What happens in one step of dt, let's say that this thing was initially headed sort of up and to the right, like we saw here a moment ago. In the one step, it says, okay, I'm going to calculate where I need to be, and the calculated value, let's say, is over here. This was the x new value that we had calculated. And so what we need to be able to do is detect when we crossed over that line and say, don't actually cross over that line, flip as though we had a perfectly elastic collision. And so in this case, the perfectly elastic condition or collision means that this distance is the same, just on the other side of the wall. So the actual position is over here, and we should have gone like this. So let's label a couple of these. We'll go nice and red. I'm going to call this delta x and this delta x. Those have to be the same thing. They're just different directions off of the wall is equal to 1. The y coordinate we don't have to adjust at all. So the y coordinate, or I should say the y change, if you go from here to here, that is okay regardless of whether it hit the wall or not. So we don't have to do anything to the y. But we have to update the x, and somehow we have to use that knowledge of the delta x to do it. We're going to call this point over here temporarily x new prime. The prime is going to indicate we bounced off of a wall. So how do we do something like that? The x new prime, this is the math part, it has to be equal to wherever the wall is minus whatever this delta x is. And we can calculate both of those. So the wall, if we just call that x wall, and then subtract delta x from it, that's the general form. For our specific case, for the right wall, we can substitute in a few values for this and say that x new prime, the wall is at 1, and the delta x is equal to x new minus 1. This x new minus 1 came from, we saw the x new is here, and we knew it was relative to that wall here, so we subtracted off wherever the wall was. We can combine those then, and I'll scroll up a little bit so I don't overwrite here on Twitch. This ends up looking like 2 minus x new. That's one of the corrections that we have to do. That's a wall correction. The other thing that we have to do is adjust the velocity. So previously our x velocity was headed towards the right, but now if we imagine our velocity is here, instead if we leave it unchanged, we'll continue off to the top right, and that'll screw everything up because it'll move us back behind the wall and then take us out of the wall, and then move us back and then take us out, et cetera, et cetera. The y velocity doesn't change, but the x velocity has to get reversed. So if this velocity down here, if the x component was u, and it was u over here, this has to be minus u, because now it's going in the opposite direction. Remember, we're only interested in x right here. All of this still holds for the y as well, except none of that has to be changed if we're reflecting off of the right wall or the left wall. If we were to reflect off the top or the bottom wall, all of these concepts would hold, except wherever you've got x's, those become y's, and wherever you've got u's, those become v's. So the concepts are still there. So the other thing that we have to do then is also reflect and say that u is equal to minus u. So these are our two conditions. Or I shouldn't say those are our two conditions. Those are our two corrections, right? We correct a position and we correct a velocity. The condition is the part that we now have to spend a little bit of time introducing because we haven't used these tools before. What we need to be able to do is detect when this x new has become greater than 1 and tell MATLAB what to do when we experience that. The short answer is we need an if statement, and we just ask if x new is greater than 1, do these corrections. The not really annoyance, the flexibility of the if statement is such that you can get a lot of different behavior just by the way that you structure the if statement. And so that's what I want to spend about 10 minutes or so talking about, is how if statements can be structured in MATLAB. And it's not just MATLAB. Most if statements that you would ever encounter can be structured in this way. The general syntax of an if statement is something like, if a condition is true, then do something. And then we end it. There's a couple of elements of that we have to work on. One is what are the conditions that we can create, right? How do we make comparisons? How do we make things be true or false or something like that? Some of them are kind of, I would guess, somewhat self-evident, things like greater than or less than. There's greater than or equal to, there's less than or equal to. Those are all have the same meaning that you're familiar with from math. They just make that comparison. A couple that are unique to coding that don't at least appear in this state in math is an equality, which is what we think of in math when we say is one thing equal to another. But when we're coding, we have to distinguish it from the assignment operator, the regular equal sign that we've been using so often. And so if you want to check for numerical equality, you just do a double equals. You can also use a tilde for a negation, which is also called a not. It's the tilde symbol, which for me is next to the 1 on my keyboard. And so you can take the negation and combine it with stuff. Most often, the only time that you see it is not equal to. There's no reason you couldn't use it with a greater than or less than, but I mean, typically people just switch the symbol, right? If it's not greater than, then it must be less than or equal to, so they just use the appropriate symbol. But there's no reason that you have to. Typically, we don't have to say the true part. Don't have to specify true. So for example, all of the following are equivalent statements. You could have something like, is A equal to 1? Right? That's checking whether or not is A true. That is fine, right? You can write it like that. But you can also just have A, right? And that will do the same thing. So if you're considering the syntax, you could say something like if A equals 1 versus if A. These are the same thing. So you don't always have to do something like that. You don't have to specify, is this true or not? You can just ask if A, and MATLAB will interpret that as if A is true, then do the following. You can also compound your conditions. And there are two ways that we typically do that. One is the double ampersand, which is an and. So that requires both of the statements to be true. So for example, something like A is equal to 4 and B is equal to 6, right? You can combine statements like that to make your conditions a little bit more detailed. It's not like something you would just pick randomly to do. It's just, does my code need something like that? The other one is or, which are the pipes. The pipes are, for me, above the enter sign, enter key, on the backslash. That's where they are on my keyboard. Same idea, if I had something like A is equal to 4, I could then put pipes between them and say B is equal to 6. And that net result would be true if either one of those were true, and similarly for the and. The parentheses that I have on there are not strictly necessary. MATLAB will interpret it just fine if you leave the parentheses off. I'm just in the habit of doing it because it helps make my code more readable. But you don't have to put the parentheses on there. It'll still evaluate it correctly. Both of these are called short circuit, which might be a new term. They only evaluate what's needed. So if, for example, you're doing the and in that first one where A is 4 and B is 6, if it immediately recognizes that A is not 4, it will never evaluate the second one. It will never even bother to check whether or not B is 6. Typically, the short circuit ones are good enough. And they can actually be really useful because you can put a quick check up front, and then if the second check takes computationally more time, you put that second. And that way it does the quick check first, and it never bothers to do the longer check if you don't need to. But for everything that we're going to do, there's really no difference. It's not going to be significantly faster one way or another. There are the other ones, which I don't really know the name other than they're not short circuit operators. You can also use a plain old ampersand and a plain old pipe to force both conditions to be checked. Usually MATLAB will complain if you try to do this, because it will say, you know, you're kind of wasting my time here, because I can actually make the decision faster if you use the short circuit operators, the double ampersand and the double pipe, because then I don't have to waste my time. Once I find out something is good enough, I can just stop there. It doesn't mean that you're going to cause any problems. You're not going to blow up a computer just because you don't use the short circuit operators. So that's how you can set that condition up there. But the way that the if statement chooses to make an event occur depends on how you structure the if statement. And so we're just going to enumerate the 4 of them here as examples, because by the time I generalize them, it would have been faster to just do them. Okay, so the plain old if statement, we could set this up as something like if condition A. What do I want to do? I don't know, something called event A, right? Some event that is related to the condition A. This has a couple of different meanings. First of all, nothing must happen. It's okay for nothing to happen. If condition A is not true, then event A will not occur, and the code will just keep going. It's not that nothing else had to occur. That's the most straightforward one, right? It can happen, but it doesn't have to happen. If you compound them and you say if condition A, we'll call that event A, and then you put an end after it, and then you say another one like condition B and event B with an end. What this means is neither event A nor B must occur. They might occur, but it's okay if they don't. More generally, this means nothing in general has to happen. Nothing must happen. Right? A might happen, B might happen, but it's okay if nothing happens too. And then a key feature of this is that both condition A and B will be checked. You may or may not want condition A and B both checked. They might be mutually exclusive, and that's where the other statements come in. So another way that we could write this is if condition if condition A, go ahead and do event A, else do event B. Actually, we'll call it C just to separate it from the other ones so that you don't think that they're the same. In this one, something must happen, either event A or event C. Event A or event C must happen. The reason that it must happen is because of the else that sits here, right? That covers all of the other cases. Condition A can either be true or false. This is defining that something will happen in both of those cases. And that may not be something that you want. So for example, with our wall reflection, just because it does not reflect off of the right wall doesn't mean that there's something that we have to do. It just means, well, it didn't reflect off the right wall. So for our reflections off the wall, we're probably going to stay away from the else statements because we don't want to do anything special when it doesn't hit, right? We just want things to continue the way that they have been before. In this one too, only condition A is checked. So there, you don't have to define another condition for the else. That's what happens if it's not A. Yeah?
So we would use else if we want to make something that doesn't fit condition A do something special?
If you want to force something to happen in the event that condition A is not true.
Okay.
The last two, I know there's a lot here. We can say if condition A, give us event B. There's another one called else if, and then you have to give it another condition. Oh, sorry, that first condition was supposed to be A. This one you can compound as many as you want. So let's throw another one on there and say condition C, and this is event C, and then put end on here. Remember, code operates from right to left and top to bottom. So when Matlab encounters a statement like this, the first thing it's going to do is check condition A. If A is true, then event A will happen, and none of the other ones will happen. It won't even check any of the other ones. If condition B condition A happens to be false, it'll fall through to the next one and say, okay, well, let me check condition B and see if that one is true. If that one's true, it'll fall into event B. Otherwise, it'll skip down to check condition C. If condition C isn't true, it'll just stop. So in this case, conditions are checked from top to bottom. Only the first condition, or first, well, let's say everything after the first. Everything after first true condition is ignored. So you might check condition A and condition B, but you'll never get to see if B was true. And since we don't have that statement, it's okay if nothing happens. Nothing here is required to happen. So your code can encounter all three of those conditions and say they're all false, so I'm not doing anything special. I just go on to the next line. And then the last one is you can compound all of these. I'm just going to copy paste all of these. You can throw an else onto here as well. A plain old else, and this would be event D. Here, because we've used the else, something must happen. Specifically, it has to be event A, B, or C, or D. A or B or C or D. Notice they're exclusive too. You can't have more than one event occur in a statement like this. You can only get to one or the other, but only one. The reason I bring that up is because this statement, the way that I've structured that, often looks very similar to the one that I defined up here, where you just slap if conditions after one after the other, after the other, after the other. In this kind of a statement, both A and B could potentially occur, depending on conditions A and B. But if you use the else ifs down here, these are mutually exclusive events. You can't have more than one of those events occur. So even though those codes look very similar and they kind of read the same when I'm reading them out loud, they behave in different ways. None of them are right or wrong. It's just different kinds of flexibility that you would need for your code. The one that we want for our ideal gas simulation is this one. The reason that we want that one is because we want to be able to check all of the different wall conditions independently. The reason being, initially you might say, well, but if I hit the right wall, there's no way I'm also hitting the left wall. So why not just check one wall at a time? Can anybody guess a time where you might need to check two walls? In a corner, yeah. If you're headed out towards the corner, you might go over both the right wall and over the top wall. And so you need to be able to check both of those separately. You can't say, oh, I went past the right, I'm done, I don't have to check any more walls. You may have gone past the other wall as well. That doesn't mean that this kind of an if structure is any better or worse than the other one. It's just different, right? That's the behavior that we want. There's no way to pick which of these is right or wrong until you have a particular problem in front of you. And occasionally I just pick one and start coding that one. And maybe I'm wrong, right? And I come back and I encounter some unexpected behavior and realize it's because of the if statement that I chose. So we're going to end up having 4 different conditions, one for the right wall, one for the top wall, another one for the left, and another one for the bottom. So I'm going to code up the right one now over in MATLAB using this syntax, and then we're going to come back over here at the end of class and talk about the multiparticle system. So let's switch back over to MATLAB. By the way, an if statement can do everything that a switch can do, but not in reverse. You can make an if statement behave the same way that we saw a switch statement does, where a switch statement, we just enumerated the cases, right? There was like case 1, case 2, case 3, case 4. You can get exactly that same behavior from an if statement, but you can't go the other way around. A switch can't do everything that an if can do, primarily because of that complication that we just saw, where the behavior changes based on how you write the statement. So the things that we did here were get the old values. This, by the way, is the same script that we started with finished with last class, so I'm just building on top of that one. We got the old values. We updated the positions with conservation of momentum. That was Newton's law. And I had previously mentioned in our pseudocode, if you go look at the pseudocode from lecture 12, there was another step that had to go here, which we skipped last time, that we'll now do. Now we'll check for wall collisions. And then only when we're all done will we store those positions. When you have to do this sort of a setup and you have to do some checks on values that you calculate before you store them, this kind of a syntax doesn't work quite as well, where you do the indexing on both sides and you just immediately do the calculation and store it. This doesn't allow you to do any checks, right? It just says that's the stored value. If you split those apart, yeah, it takes a little bit more writing, but it's a little bit easier to see which one is which. So we'll start that right wall first. And what we want to do is check to see whether x new is greater than 1. Did you go beyond the wall? That's what you're asking MATLAB to say. We're going to close it with an end statement. And then remember, we have to update 2 things. We have to update the position and the velocity. If we write it out fully the way that we did by hand, we would say something like x new prime is equal to 2 minus x new. This corrects the position. But we saw a cleaner way to write that previously when we were talking about the idea that code executes from right to left, and that equals that we use in there, that's an assignment operator, not an equality. So because the thing on the right is going to represent the new value of the thing on the left, but conceptually they're related, right? It's the same new position of the particle, we just reflected it across the wall. We can get away with that sneaky way of writing it by just saying x nu is equal to 2 minus x nu, which algebraically doesn't make any sense, but the computer reads it as the first thing I do is calculate 2 minus x nu, and then what do I assign it to? Well, I just overwrite the old value of x nu, because I don't care about that value anymore. Similarly, the velocities, we can just say u is equal to minus u, right? It'll determine the value of u on the right, it'll put a negative sign in front of it, and then it'll overwrite that value of u again. So we use that sort of clever notation for computers that doesn't work in algebra to save us writing intermediate variables here. So this was correct, the velocity. So let's run that and see what our thing gets. It appears to have worked okay, but it looks a little bit weird. So we see we took the first step okay over here. We went from our initial position over to here. Then it looks like something broke a little bit, right? Somehow we took this vertical step that doesn't look physical. Part of the reason of that, nothing broke here, everything worked the way that we wanted it to, but remember, whenever anything plots something, it always just connects everything by straight lines. So it doesn't know that that particle used to be over on the right and that it actually went to the wall and bounced off. All it knows is that those were the two positions of the particle, so it connected them by a straight line. If you didn't want to be kind of confused by the straight line quite as much, don't draw the straight line, right? If you, instead of b dot dash on your plot, if you say b dot, or better b circle, and now draw it, in your mind, now you can track what's happening, right? I was here, and then I was here, then I stepped and went too far over to this side, and it got reflected back to where I needed to be over here, and then I started stepping off in the other direction. If you take smaller and smaller time steps, it'll look more and more like you would expect it to. So I turned it back to its wall, or to its dot. If we take 0.3, it looks like this. If we take 0.1, it gets a little bit closer, right? Now it looks a little bit more like a reflection. If we say 0.1, then we don't actually get to the wall, so we have to up the number of steps. So let's do 100 steps. Now it really starts to look exactly like we would expect, right? We can't tell that it didn't actually go beyond the wall because, in fact, it never did, right? Our calculation corrected it before it got too far. And now if you replace this and get rid of the dots and draw it as a line, the finer the time step, the more it looks like an actual collision with a wall, right? A nice elastic collision that bounced off in the way that we wanted it to. But it's still there. If you zoom in on that point, you'll see that it still looks kind of funky right in that regime. But you got to go way in before you see it. In fact, we actually went too far in. Well, we clicked on it or calculated it enough that I actually can't see it at this point. So you can see kind of the trade-off, right? It takes more calculations, but the result is a little bit better as we go. So great, it worked just fine. Now what we're going to do is we're going to take about 10 minutes. We'll go till about 3:45 or so. And what I want you to do is code the left, the top, and the bottom wall. And you'll know it if you got it right. If you keep increasing the time, so for example, I know this one is wrong, because if I increase the steps, let's say to 1,000, it just goes right off the side of the domain. So you'll know your code is correct when you keep increasing the number of steps, and it starts to look more and more like a billiard ball bouncing around inside of there, right? Equally off of every wall that you've got. So I'm going to shut up. We're going to go about 10 minutes or so. We'll be back at about 3:45 to finish up that coding. Actually, we'll come back a little bit before that, say 3:42. And then we'll look at the multiparticle system. All right, if I wanted to code up the top wall, I'm going to pick the top wall first because it's very similar to the code that we've got for the right wall. It's just I replace the x's with y's and the u's with v's. That's easier said than done a lot of times because you'll say it in your mind and then you'll be reading the code right above it and you'll accidentally put the wrong variable in there. So just be careful if you do something like that. So we're going to check if y new is greater than 1. That is asking MATLAB, did you go beyond the top wall? We end it, and then we do the same kind of calculation. So we would say y new is 2 minus y new. So that's correcting the position. And then we would say, this is where I would make a mistake, right? I might say something like u is equal to minus u. Right, if I'm just reading the code above it, I'm in the habit of not reading very carefully, and so I might make a mistake like that. Or maybe I'm smart enough to like know some of it, but not others, right? Maybe I said v is equal to minus u. So just be careful when you see that similarity between if statements that you update them all correctly. It's easy to make typos in there, and I only say that because I do it all the time. So then we'll go on to check the left wall. This time the condition is different. The left wall is at 0, so we check whether or not x new is less than 0. That would mean we're over on the left. That's our left wall check. If it is there, the formula that we need is actually the same as what it was previously, but because the wall is located at 0, this simply becomes minus x new. But if you go through the same math that we did for the right wall and just replace the 0 for the wall position, you'll get that formula. And then u is equal to minus u, and then finally the bottom wall is if y new is less than 0, then set y new equal to minus y new, and set v is equal to minus v, and finish that. If we go ahead and run that, you should get some polygon-looking things, and kind of remind me of those the DVD screen players where they go towards the corner. You can now answer the important question of what's it take to land in the corner. You can simulate the initial conditions and the initial velocities to get your thing to hit in the corner. But this is an ideal gas. As far as an ideal gas is concerned, the only thing that exists are the boundaries of its container. And even that, an ideal gas probably doesn't think that those really exist. We just impose that condition on an ideal gas. So that is, as far as I want to take a single component of an ideal gas, that's enough to do the simulation in the homework, both problems 3 and 4. It's also enough to handle the simulations that I'm going to ask you to do on the midterm. Everything that you can kind of put a mental block right here and say, that's all I need for the midterm. The things that we're going to go doing forward, or things we're going to do going forward, may be of help. It may be a way for you to do them if you like that particular method. But it wouldn't be required. This is enough to do everything that is on there. Before we start sketching out the multi-particle stuff, any questions on that? Because I think what we're going to do from here on out is probably just sketching out ideas. We probably won't keep coding. Yeah?
Could we sketch the top and bottom wall collisions as mutually exclusive?
Potentially. So can you think of a reason why it could be a problem to do that?
Time scale is like really large.
Exactly. Or if the time scale is really large, or the velocity is huge. So if you get to a position where somehow you step more than 1 unit length beyond the box, I mean, generally you're kind of screwed anyway. Like your simulation's not built to be able to handle that. And that's the source of a lot of like glitch speedruns and stuff like that, where for the most part the physics work fine, but if you can get the machine to be in a particular state, you can get weird things to happen. And typically we don't worry about that. So something on your homework is going to happen there too. You'll have 2 blocks colliding, but there you make an assumption very much like what you just said, which is only one of those is going to happen. I never have to worry about the block hitting another block and the wall at the same time. So we treat them as mutually exclusive. In which case you could do the if and then else if and then else if. Here we do the separate ifs to handle the corner. And that's as far as we go to handling weird situations. Okay, so multiparticles, the idea is very much the same, right? We got to do that, but we got to do it for a lot of particles. So it's going to increase the complexity of the data structures that we're dealing with, but conceptually, it's that. It's just that a bunch of times. So let's sketch that out, what that would look like over here in Excel. Multiple particles. The biggest change is the data structure. So the data structure for the trajectories is now a matrix. And the way that we're going to set that matrix up is to build on the vector that we had before. So previously, we had said that the vector x looks something like this. We had said the particle, we'll call it particle 1, is here. And then we said time 0, and this was time 1, and this was time 2, and time 3, et cetera, dot, 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 all the way down to whatever the last time happened to be. Or the simulation step, right? It didn't really matter which one was which. And we had started this off with its initial position, and then we had calculated the rest of these as we go. We're going to do the same thing for multiple particles, but instead of one column, we're going to put another column next to it. So that'll be for particle 2. And then we do exactly the same thing for particle 3. We're not going to go beyond particle 3 because we're going to set it up in such a way that we can just add more particles arbitrarily. But what Matlab is going to see is just this inner part, right? It's going to be all of these numbers. And initially, these are all going to be 0. And in fact, the top row will be as well, but the top row here will be your initial x positions. Right, that we'll have to go through and update those positions as we go. And similarly for y. We're not going to write out y, but it's going to look basically like this. And then each time we go through a simulation step, then the time gets a little bit longer, then we update another row of zeros, right? But every time we take a time step, we have to update all of the positions across that entire matrix. The velocities used to be just a single number, right? We would say, I don't know, 0.4 here. We have a choice. We could either put more velocities going up and down, but to keep them consistent with the way that we did up here, we're going to keep them in rows. So we're going to have, keep it as a row vector, which means we're going to add columns. So maybe this one is 0.2, and maybe this one is minus 0.5. All Matlab is going to see, again, is just the values, right? So I'm boxing the data structures that Matlab will see, and it'll look like that. Similarly, the V will look pretty much the same as this, right? It'll just be different values. So minus, I don't know, 0.7 and 0.05 and something like that. We'll just leave the last one the same. So these will be row vectors. Could they be column? Sure, but it'll help our math actually if we leave them as rows. Are the pseudocode that we're going to use? It still starts off with initializing stuff. If you can spell that right, initialize. The initialization will have to be a little bit different. We also, in addition to everything else, have to specify the number of particles, whereas previously we only had to specify the number of steps. But now we have to do both. We're going to pick 3 here, but we'll do something else. We're going to initialize all of the x0 values, all of the y0 values, all of the u, and all of the v. And these are going to be random numbers from 0 to 1. The reason for that is because if we suddenly jump from 3 particles to 50 particles, I don't want to come up with 47 random directions and random velocities and all kinds of stuff like that. We'll just draw random numbers and keep them between 0 and 1, and that'll go in the direction that we want. The next part's the simulation, which is the iteration. And that's probably the biggest change. Now we need a loop inside of a loop, which is something that we saw on homework 2. So we say something like for each step, And then when we're inside of each step, we then have to do for each particle. And what do? We update their positions, and we check for collisions, and we store the result. Which conceptually looks similar to what we were doing for one particle, except now there's this extra for loop that sits in there that we can go over all of the particles each time. And then last is the analysis, and we'll stop here today. That is probably going to need a for loop, at least initially. We're going to say for each particle, plot x, y. We'll have to add the remainder of that code, right, so that they all show up on the same figure so that we can actually see them all bouncing around on the same place. But it's going to look, again, this is pseudocode. It's going to look something like that. We'll have to correct things around the edges. So this is where we will pick up on Friday. We'll just start from a blank slate on Friday and then compare the results after we're done. So I'll wrap it up here. Don't forget, tomorrow during the lab hours, you can either show up on Zoom if you want to do the remote version, or you can show up physically in here during any of those 2-hour periods. And I'll be hanging out in here. Stop by and work, ask questions, whatever you want. Otherwise, I'll see you back here on Friday.